Hello everyone and welcome. In this video we'll be looking at the quick sort algorithm, and in fact we'll be looking at the in-place version of the quick sort algorithm. Now the quick sort algorithm is a very complex algorithm to write, and you'll see that in a later video which I'll post but it is more efficient than insertion sort, which is of course more efficient than merge sort, which is of course more efficient than the bubble sort algorithm. Now the way the quick sort algorithm works, the in-place version which I'm going to be using here, we'll have the left pointer and the right pointer right there. So we have left pointer and a right pointer there. Now this left pointer and right pointer will keep moving either to the left or the right. So we'll keep checking if the value in the left pointer is smaller than the value in the right pointer. If it is, the left pointer will keep moving. If we swap at any point, so where the left pointer is larger than the right pointer and we swap, then we alternate and we start moving the right pointer. If there is a need for us to swap again, where the right pointer is smaller than the left pointer, we'll swap again, and we'll keep swapping until the left pointer and the right pointer are on the same index position. When this happens, that value there will be in place. So let's demonstrate it using these set of cards. I want you to imagine that this set of cards are in a list. Our left pointer will be in the indexed position of the first value, which is 0, and our right pointer will be in the index position of the length of the list -1. Again, I'll just remind you that we're using the length of the list -1 because we don't quite, so if you look at this list, we have 7 items in this list. Now we should remember that the index position of the 7th item is actually 6. So if we were to look for the index position of the length of the list, we'll look for 7, and 7 does not exist. Okay, so how does this work? We compare 2, which is the value in the left pointer, and 6, the value in our right pointer. We can of course tell that 2 is smaller than 6, so our left pointer will move 1 place to the right. Okay, and then we compare 7 and 6. Now 7 here is larger than 6. Because 7 is larger than 6, we would have to swap. In this case, I'll just remind you that most times when we swap values in a list, there is a need for us to make use of a temporary value, temporary variable, to allow that swap to happen. Of course, some programmers will say we don't have to, and they are of course right. So I'm going to take this out, and then because 7 is greater than 6, I would swap them around. Okay, so 6 comes there and 7 comes there. Now, because we have swapped, we will then have to move our right pointer 1 place to the left. Okay, so technically we're taking 1 away from our right pointer, and at this, our right pointer will then move there. So we'll then compare 6 and 1. Of course, A there represents 1. 6 and 1. Now 6 is larger than 1, which means we have to swap. And when we swap again, so A goes there and then 6 comes there, the pointer that's moving would change. So our left pointer would increment by 1 and then move 1 place to the right. Okay, and then we compare 3 and 6. 3 is smaller than 6. We'll move on because we haven't swapped. There's no need to change the pointers moving. 5 is smaller than 6. We'll move on. 4 is smaller than 6. Of course, we'll move on. And then 6, our left pointer and our right pointer are on the same index value, and then we'll stop. Now this is a highly recursive algorithm, but the in place makes that boarding on memory quite low compared to other versions of quicksort algorithm. At this point, really, you would notice that all the values on the left hand side of the value in place, so 6 is currently in its place, are larger. Sorry, all the values to the left hand side are smaller than that value, and all the values on the right hand side, if we had more than 7 here, this value here, will be larger than 6. 6 is now in place. Now, because this is a recursive algorithm, we will then repeat this process for the leftmost side of our list now. Okay, we'll repeat this for the leftmost side. Again, we'll compare 2 and 4. 2 is smaller than 4, so we move our left pointer there. Okay, now A or 1 is smaller than 4. Again, we'll move our left pointer. We're not moving the right pointer here because we haven't swapped. 3 is less than 4, so we move again. Now, if you see here, 5 is greater than 4, so there is a need for us to swap. If we swap these around, we'll then move our right pointer here. You can see here 4 is now in place. Now all the values on the left hand side of 4 are smaller than 4, and all the values on the right hand side of 4 are smaller than 4. Now let's not forget that if I'll do something here. So far 6 and 4 are the two values that are in order and in place. So technically these two values are the only values really that are sorted. We still need to check these other sub values, and that's what really makes this algorithm a very complex algorithm to write. So if I then go on to these next sub list, I would then look at these values again, compare 2 and 3. Now 2 is smaller than 3, which means my left pointer would move. 1 is smaller than 3, which means my left pointer would move again. At this point, 3 is now in place, and then that means we now have 3 values, 3, 4 and 6, that are in place. And I'll repeat this for these two. Now these two, left pointer, right pointer, if I compare both of them, 2 is larger than A. I'll move them, I'll swap. Because I've swapped, my right pointer would move, and once my right pointer moves, both pointers are the same. A is now sorted. I'll repeat this for the other parts of our list. Now it might be the case that inside or in between this sublist you could have more, but in this case what we have here is that left pointer, right pointer are the same. This becomes in place. Left pointer, right pointer the same. This becomes in place. Left pointer, right pointer the same. This is in place. And technically speaking, all the items in our list are now sorted in ascending order. So this is how the quicksort in place version works.